In the first session, we saw how Eudoxus, Euclid, and Archimedes looked at curved areas by trying to figure out the relationship between various elements of the curve, specifically a circle, with respect to diameters and areas. So here what we are going to do is look at how integrals solve the same problem. So the figure formed by a curve bounded by the curve x-axis and the vertical lines at the endpoints of the curve is not rectilinear. We can arrive at a good approximation of the area under the curve by overlying rectilinear figures over the area bounded as mentioned above. So given the function, plot the graph. So let's plot the graph of this given function. Let's say this is this f of x, where x is between a and b. If not given, mark the endpoints as a and b. So a and b. Draw lines a and b perpendicular to x-axis from a and b. So this is a. So this is the line from a perpendicular to axis, and this is the line from b perpendicular to the x-axis, and they intersect the x-axis at a and b. We have arrived at a bounded figure AABB, bounded by the curve f of x, x-axis AA and BB, whose area we have to find. Now, draw a rectangle on AB with height AA. Area of this rectangle is a very rough approximation of the area of the figure. So this is the rectangle we are talking about. And this, when we compare this area with the area under the curve, it gives us an approximation, yes, but it's not a very good approximation. So to get a better approximation, what do? We take the midpoint of AB and draw rectangles on those two parts. So on those two parts of that, we have drawn the rectangles. Is it a good approximation? Actually, I think it's a little bit worse than before. So let's increase the number of rectangles to 3, 4, 5, 6. So do you notice that the difference between the area under the curve and the sum of these rectangles is reducing? So this is what the step says. Take the midpoint of AB and draw a rectangle. Start from A. The upper left corner of the rectangle is on the curve f of x. The sum of these two rectangles is a better approximation of the area AABB. That is when we had two rectangles. But as we keep increasing the number of rectangles by dividing the line segment AB into smaller and smaller equally spaced segments and drawing rectangles on them bounded by the curve, what will happen? The area derived by adding up the areas of these rectangles will be a better and better approximation of the area under the curve. But it will always be an approximation. Why? Because either it will be overestimated or it will be underestimated. If we keep taking more and more and more and more rectangles, you see this gap keeps getting reduced. But it remains. Now to actually get the area under the curve exactly, we will have to take the number of rectangles to infinity. The area under the curve becomes equal to the sum of the areas of the rectangles in the limit as n goes to infinity, where n is the number of rectangles. So let's see what happens as we keep increasing the number of rectangles. So I am at 29 now, 30. Let's take it further. 75. I'm at 161. 186, 200. Now let me directly take it to 300. It is still an approximation. Remember, I can't actually take it to infinity. What this says is that as I keep increasing the number of rectangles higher and higher, the area becomes a better and better approximation of the area under the curve. Of course, if we take it to infinity, it will become exactly equal. Now, let's actually work through this. This is the explanation part. Now, let's look at how exactly we arrive at this. Now, let n be the number of times the segment AB has been divided equally. The width of each interval is, let's say, delta x equal to the segment AB divided by n. Or we can say x value of B minus x value of A divided by n. Let's have a smaller number of rectangles so that I can refer to it. The endpoints of each interval, that is, intervals are these. Each of these are equally spaced, which means delta x, each one of this is a delta x. So the endpoint of each interval, here we are taking the left endpoint. So A is x naught, endpoint of the second rectangle on the x-axis is A plus delta x. Remember, this distance is nothing but A. X2, that is this one, this point, is what? A plus 2 delta x. This point is A plus 3 delta x, and so on. And in general, x sub n minus 1 is equal to A plus n minus 1 times delta x. Why that n minus 1 is? Because we are starting with 0. Each rectangle has a height f of x sub k minus 1. So here this will be, this point is what? In general, it is A plus n minus 1 delta x. Now for this point, we want the intersection of the rectangle with the curve. So each rectangle has a height f of x sub k minus 1 and width is a constant delta x for all rectangles. So this is f of x sub 0. This is f of x sub 1. This is f of x sub 2 and so on. So length into breadth will give us the area of the rectangle. Now area of each rectangle is equal to f of x sub k minus 1 times delta x. Now we sum it up. So sum of all the rectangles, let's say S sub n, is equal to summation of k equal to 1 to n of f of x sub k minus 1 times delta x. And this is called the Riemann sum. As we increase the number of partitions, what will happen? The number of divisions will tend to infinity. And what will happen as I keep increasing the number of subdivisions to infinity? The delta x, that is the base of each rectangle, will keep getting reduced. Yes, we saw that. So that will tend to 0. So we put it as a limit statement because we can't actually go to infinity. We can only tend to infinity. It's like saying we can never be perfect. We can always strive for perfection. So we say area is equal to limit as n goes to infinity of summation k equal to 1 to n of f of a plus k minus 1 delta x times delta x. Now, where did this come? This is from the general formula. So this gives us the sum of all the rectangles as the number of rectangles goes to infinity. Please compare this with a method of exhaustion by Eudoxus, which was used by Euclid and Archimedes, especially Archimedes for finding the area of a circle. So here what we are having? We are having, instead of rectangles, we are having triangles. We are increasing the number of triangles by increasing the number of sides of the polygon that is being inscribed in the circle. Okay. Now here, very interestingly, you have something called as left, right, and midpoint Riemann sums. So what that basically means is, say, if I have these three triangles, left Riemann sum means we start with the A position, x equal to A, and we take f of A, and then we draw a line parallel to the x-axis and drop a perpendicular line to the first point of the division. Now it intersects here. So from here we draw a rectangle. We take this line upwards and again we draw a line here. So here our focus is on the left upper point on the curve of each rectangle. The other is right. So here what we do is, we don't start with this. We start with the right. So this point. And we draw a rectangle towards the left. We take it. Now we take it here. And we draw a rectangle here. Then we take it here and draw a rectangle here. Midpoint. Now instead of taking left or right, we take the midpoint. So this would be the midpoint. And we draw a line parallel to x-axis. And draw the rectangle. Then we take the intersection, the midpoint here between these 2 points, and yes, and draw a line parallel to x-axis. Then again we take the midpoint and so on. Keep doing. By the way, the diagram that I have shown is the left Riemann sum. Now, irrespective of which Riemann sum is chosen, left, right, or midpoint, as n goes to infinity, left, right, midpoint sums converge to the same area. Now, look at this notation. It's going to be painful, no, to write this every time. So, we simplify the notation. So, we combine this limit as n goes to infinity and the summation into a single, this one, elongated S. And we substitute this with just f of x. And instead of delta x, we say dx. This is the notation for indefinite integral. Now, in case of definite integral, f of a is the area accumulated up to a, usually taken as 0. So, if we are talking of this, up to a, from minus infinity to a, the area accumulated is 0. Yes. Then we take capital F of B is the area accumulated up to B, that is from minus infinity to B. So since up to A it is 0, so that means F of B would be this. So if we subtract these two, we get the area under the curve. But remember, I have restricted the curve. If it was a continuous curve, you know, before A and after B as well, then area accumulated up to A would be some value. So in which case also f of B minus f of A would give you the area under the curve from A to B. So the notation changes a little bit. We have the elongated S and we define the limits from A to B of f of x dx equal to capital F of B minus capital F of A. So here, remember, we are talking of area under the curve from a point A to a point B. So we are talking of definite integral. In the next session, we will look at indefinite integral. How to arrive at the expression for this integral f of x dx equal to what? That how to arrive at we will look at in the next session. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.